Hey everyone, and welcome to this Forge College Explainer. Seriously, I am so pumped to have you here today. If you've been grinding away in our Solidity from zero track, you know we've been building up our skills piece by piece, gear by gear. Well, today is a massive milestone. We've hit the point in our capstone project where we finally get to assemble our smart contract components into a living, breathing machine. So let's jump right into assembling and refining a project increment.
Now, right off the bat, I've got to give you some credit for the hard work you've already put in. In our last explainer on debugging and test strategies, we went through some downright grueling debugging sessions, didn't we? You isolated faults, you wrote unit tests, you patched up those individual gears. The hard part? It's done. So today, our goal is basically the master inventor's dream. We're going to take all those perfectly polished gears, build our final machine, and, most importantly, turn the whole thing on without, completely blowing up the lab.
Okay, let's dive into this blueprint for today. We're going to hit the assembly line, wire up our components, sequence some modifiers, tune the whole thing for gas, run a quick integration stress test, and finally, prep for the final handoff.
All right, phase one. Welcome to the assembly line, where we start putting the pieces together.
Listen, before you just start blindly bolting things together, you need to gather your verified inputs. I'm talking about your requirement map, that function responsibility chart, your helper libraries, and definitely those debug reports from our last session. These artifacts right here, they are your absolute source of truth. They tell you exactly what responsibilities belong to which functions, and having them handy is going to ensure this new assembly line of ours produces exactly what we designed. No surprises. Moving right along to phase two, wiring components and adapters, and making sure those gears actually fit.
So it's time to stitch those verified components together. Look, in a perfect world, every single function signature perfectly matches every library call, right? But we build in the real world, and that's where the adapter function comes in. Honestly, you can think of this as the duct tape of Web 3. When two perfect gears have slightly mismatched teeth, say your library expects an array but your contract is spitting out a single integer, an adapter function is that super thin layer of code that bridges those mismatched function signatures or return semantics. It just smooths the whole thing out.
Now, what's really interesting about this slide is how it illustrates a classic developer trap. On one hand, you've got the dreaded square peg and round hole, mismatched signatures that are literally going to cause your compiler to scream at you. There's no way around it. But the elegant solution? That's the adapter function. It gracefully routes the data, keeps your core logic completely clean, and totally isolates all that messy translation work. It is an absolute lifesaver, for sure.
Okay, phase three. Sequencing modifiers for security. Or, as I like to call it, calibrating the safety valves.
Obviously, we want to ensure our machine isn't just functional but utterly secure. So the crucial point here is sequencing. The order in which you stack your modifiers fundamentally changes how your contract executes. Just look at this sequence on the screen. Step 1 is our validation guard, checking our preconditions. Step 2 is collecting fees. That's a side effect. Now, you definitely do not want the vault opening to collect fees before the security check even runs. That would be a disaster. The order is literally everything.
Let me ask you a quick question. What do you think happens when an only owner modifier and a non-reentrant modifier interact on the very same function? Like, which one should run first? Because combining modifiers changes the execution semantics entirely. Think about it. You absolutely want to block reentrancy before you even bother checking who the owner is. Why? Because it saves gas and prevents edge case attacks. This is exactly why adding a little comment in your code to explain your chosen modifier order isn't just good practice. It's a mandatory safety check for any master inventor out there.
Which brings us to phase 4, tuning for gas efficiency. Time to trim the excess. We want our contract to be lean, mean, and cheap to execute on the blockchain, period. And one of our absolute best tools for this is the internal helper function. If you find yourself writing the exact same complex require chains or math operations in multiple places, you're wasting gas, and you're making your code so much harder to read. An internal helper basically centralizes all that duplicated logic. Because it's tightly coupled to the contract state and marked internal, it keeps your code elegant, it drops deployment costs, and it saves your users valuable gas. Win, win, win. But wait, here is a golden rule you have to remember. Always prefer clarity over micro-optimizations. A smart contract that's perfectly optimized, but literally impossible to read, that's a dangerous contract. Actually, scratch that. It's a ticking time bomb. That being said, to pass this capstone milestone, correctly documenting at least 3 efficiency choices, like using that internal helper we just talked about, or picking a specific modifier order just for gas reasons, is what separates a novice coder from a master Web3 inventor. Be intentional and write down your reasons.
All right, phase 5, the integration stress test. This is where we flip the switch.
It is finally time to run this assembled machine and see if the whole thing actually survives the process. To do this, we rely really heavily on what we call reproducer scenarios. Remember those specific, frustrating sequences of events that caused your isolated components to fail back during the debugging phase? Yeah, those. You need to run those exact same sequences against the newly composed contract. This ensures that fixing one gear didn't accidentally just break another when they got wired together. It basically proves your machine is robust under pressure.
Let's move to our living engineering checklist and see how this builds out. Trust me, to get through this stress test without losing your mind, you need this tracker. You're going to compose your functions, wire up your modifiers, refactor that duplicated logic, and run those tests locally. Keep updating the status as you go. If a test fails, no big deal. You isolate the regression, fix it, and just run the checklist again until the whole board is green. And finally, phase 6, ready for final handoff, getting that inspector's sign-off. So to prove this increment is truly deployable ready and get your final patent approval for this milestone, you've got to meet some pretty strict acceptance criteria. Your increment must expose the core functions defined in your blueprint. It needs strict, clearly documented modifier ordering. Every single one of those reproducer scenarios has to pass. All your libraries must be compatible using those handy adapters we talked about. And absolutely no duplicated logic can remain. I know it's a high bar, but it ensures absolute, top-tier quality. The ultimate proof that you've met all these criteria is your integration report. Seriously, this is your golden ticket. It's just a short document that lists out your passing tests, notes any minor remaining known issues, documents your gas efficiency choices, and confidently declares your smart contract increment as deployable ready. Once you have this little report in hand, congratulations, you have successfully assembled your machine.
And just like that, you are ready to cross the finish line. I want to give a massive thank you to Forge College for making this explain possible. As you step back and look at the incredibly complex smart contract machine you've just fully assembled, I want you to ask yourself, what brand new, world-changing systems can you build now that you know how to perfectly integrate these complex components? The sky is literally the limit. To explore that question and to finalize your capstone project, definitely visit forge.college to learn more about this subject and a ton of other fascinating Web3 topics. Until next time, keep building, keep testing, and I'll see you in the next explainer.